Hi, this video is on exponential and log modelling questions. Learning intentions are that you understand the different forms that equations tend to be given in for these questions, understand how to interpret the information that's given in the questions, often in a worded form, particularly related to time, to understand how to apply a general method that you already have for finding an equation, and understand how to use the equation once we have it to solve various different problems. Okay. So the first thing is the form of the equations. We're used to things like um, this sort of thing, or yeah, that sort of thing. That's the kind of thing that we've had so far. And you're used to dealing with finding those problems, finding those unknowns and things like that. What we'll be looking at now are where you're given a slightly different form of an equation. So it might be something like, just get rid of that. Like that, or something like that. So the thing that's obviously different here is we have these, the notation is a little bit different. We've got these little subscripts here. What these mean are, a here is a variable, it varies, so it's like our y before, but a0 is a particular value of a. So it's just a constant, and you're going to have to work it out before you can solve the rest of the problem. That's it. So it's just like there's an extra step in finding out one of these constants. That's all. Here, just in case you get something like this, we've got a subscript here is t, meaning that as t varies, f changes, f varies as well, and these are particular values. F1 and F0 are constants in this formula, and ft varies based on these different values. Okay, so something to look out for is things like this, a0, this is sort of when t equals 0. They're basically telling you things about the initial starting conditions. So you're looking out for words like initial, start, at the start, starting conditions, at the beginning, or before the experiment, these sorts of things. Now they're the kinds of things that will be given in the description. They're the words you should be looking out for, which are telling you this is what it was like when the experiment started. And that's what this sort of thing is. It's the value at the beginning, the value at the very beginning here, f of 0, when time is 0, when time is 0. Let's have a look at that in a question. This is from your textbook, so you can look that up, page 218 in the 2010 edition. This is based on question 4H. Question 4. The decay of a radioactive element E is given by the equation E equals E0 e to the minus kt, where E is the number of radioactive nuclei present T days after the start of the experiment. If 200 radioactive nuclei are present in the element at the beginning of the experiment, and there are 33 present after 10 days, find k to 2 decimal places. So what I suggest you do is pause the video, try and work out the equation, and then come back and check in a minute. Okay, so the first thing we know is that there are 200 at the beginning. This is telling us what our value of E0 is. So the first thing we can write down is E equals 200 e to the minus kt. We're then told there are 33 present after 10 days, so 33 equals 200 e to the minus k times 10. Here, if we just say what we're doing, sub in 1033, and here sub in E0 equals 200. So just tell the people who are reading your work what you're doing. And we need to solve this. So if we rearrange a little bit, 33 over 200 equals e to the minus 10k, ln 33 over 200 is minus 10k. So k is minus 1 over 10 ln 33 over 200. Now we want it to two decimal places, so ln of 33 over 200, which is that, and then multiply that by negative 1 over 10, negative 0.1. And we get 0.18 to two decimal places. So 2 TP there. Okay, so we found K. Find the number of radioactive nuclei present after 1 day and after 5 days. Again, just pause your video, see if you can work it out first, then come back and check in a minute. Okay, so first we've got, we want to solve when t equals 1. That's our first problem. Our equation is E equals 200, so e to the minus k, sorry, we now know that's 0.18, and t equals 1. And over here we're going to solve when t equals 5. So we've got e equals 200 e to the minus 0.18 times 5. So we've got a value of here e equals, and we have 200 e to the negative 0.18 times 1, so that's going to be 167.05, or 167 to the nearest nuclei. And here we'll have, we'll just change that, so it's going to be 0.18 times 5. Oh, no, now you noticed what happened there, times the whole thing by 5. So I wanted that times 5. Huh. That's better. 81.31. Or 81 to the nearest whole nuclei. You should usually be given some degree of accuracy that you're expected to give, but if not, just use whatever you think appropriate and say what it is that you've done. So if you go to two decimal places, say two decimal places. If you're going to the nearest whole one, say you're going to the nearest whole one. Okay, next part. Sketch a graph of E against T, and then we'll use our graph, and then a couple of other questions there. The first thing is the sketch. Again, please have a go on your own first. Pause the video, see if you can sketch it. Okay, we have the equation E equals 200 e to the minus 0.18 t. This is a graph of E against T, where T is time in days, and E is number of radioactive nuclei. Alright, this is an exponential equation, so our initial equation initial graph would look like that. Has there been a reflection? Yes, in the y-axis. Here, there's a negative there. So it's now going to look like that. Dilations, yes, 2. We've got 200 in y and 1 over 0.18 in x. And no translation, which is helpful, because it means that the asymptote hasn't moved. So we can put that in straight away over here. If it hasn't translated, it just looks like that. Oh, it's on the axis. And my graph, I know, has this shape. And I don't actually have to do any more calculating for this because I worked it out before. We knew that when t equals 0, it's 200. So we've got that value there, 200. We also have another couple of values. We know when t is 1, we've got 167. So if we say 1, 167, and we've got what, 581 was it? Yeah. Okay. Estimate how long there would be. It would take till there were 50 nuclei left. So if that's 81, I'll be somewhere down here. This is very rough, and I'll just say 6 days. If you're doing this in an exam, you'd probably have a little bit more direction. You might plot it on, it's unlikely, but you might plot it on graph paper and be able to get a more accurate reading of it. But we'll leave it at that for now. Would there ever be no nuclei left? And give reasons. So this is E. So D, I'm saying about 6, maybe 7. E, would there ever be no nuclei left? Well, according to our model, no. And the reason is the asymptote. According to our model, it never actually gets down here to E equals 0. So there's never going to be 0 nuclei. And F, the half-life of an element, is the time taken for half of it to decay. Find the half-life using your equation. Pause it, please, and have a go. Okay, so the half-life is the time taken for half of it to decay. It started at 200. When half of it's decayed, it will be 100. So we're trying to solve 100 equals 200e to the minus 0.18t, and we want to know what is the time, how long. So find the half-life is a question of time. So that means a half equals e to the minus 0.18t. ln a half equals negative 0.18t. T equals ln of half over minus 0.18. So T is 3.85 or 4 to the nearest whole day. Again, just if you're not given direction, just make sure you say what it is you're doing. So 3.85 to 2 decimal places, or 4 to the nearest whole day. Right, now if we just have a quick look at what our aims were. We wanted to understand the forms that they tend to be given in. So we've got things like a equals a0 e to the minus kt, or what was the other one I said? ft equals f0 ln, something like that. That sort of thing. Understand how to interpret information in questions. So we're talking about understanding that words like at the beginning, at the start, before the experiment ran, that sort of thing is telling you about the initial conditions. So you're looking for things like A0 is the initial amount, F0 is the initial amount of F, whatever that is. Understand how to apply our general method. I hope that was fairly familiar. Just go through it bit by bit, do your little mini sketches, and it's pretty easy to build up the full picture. And lastly, understand how to use the equation. It's worth noting actually, the most common mistake that people make with these is, let's say we had a equaled e to the minus 0.5t, and you're asked to find a when after 5 days. So people sub in 5 and they get that, that's fine. And then the next question is find the amount, sorry, not find the amount, find out how long it takes to get an amount of 50. And instead of putting 50 equals, they put it straight back into time. That's probably the most common mistake that people would make. So just take your time, look at the questions carefully. There are lots of worked examples and practice ones you can do here in exercise 4H, so I would just recommend doing some of those next. Okay.